Coming to our third and last topic, I think in the future we'll see a lot more integration of different types of printing techniques and materials as well. So this is a nice example by my former colleagues from University Medical Center Utrecht, where they used FDM to lay down PCL large fibers, extrusion based, for the bony part of an osteochondral scaffold. They use melt electrowriting, which is a very up and coming technique for much smaller fibers for to reinforce the cartilage part. And finally, they used a hydrogel with cartilage progenitor cells to bioprint that gel with cells on top and make this knee cartilage tissue, articular cartilage. So we've been working on integrating techniques as well recently in collaboration with the University of Edinburgh. We've been working on some vascular grafts. So this was published a few weeks ago in Advanced Materials Technologies. So here we have first printed a Gelma hydrogel tube and then electrospin polyester fibers on the outside of it to make a sheet, and this reinforces that tube. So you see some images here where it compressed between trees as well. The Gelma is nicely autofluorescent, and then you see the outer electrospun layer surrounding it. And we did this to achieve certain mechanical properties. Here we see we've used a few different Gelma concentrations in different types of polymers. And we see here that the green dotted line is the burst pressure of native blood, native arteries, and we match the native artery burst pressure. And so this burst pressure is about 100 times higher, so it's about 100 times stronger than Gelma alone. So this thin layer of electrospun fibers really adds to it. But then what's particularly interesting is that the compliance, so that's like the inverse of stiffness, we match that as well. So these grafts have the same burst pressure and compliance as native arteries, whereas synthetic ones like Dacron and PTFE are much stiffer, which gives some problems, as many people will know. The Gelma layer also supports endothelialization, so we can grow endothelial cells on the inside, and this should really help with hemocompatibility, and this is what we'll be testing in the near future. Okay, to wrap up, looking ahead, I think the focus has been a lot on the 3D printing itself, and it's come a long way, the technologies and the materials. But I think more and more we'll start to focus on what happens with the product after manufacture. So 4D printing is one example of this. Secondly, I think we'll see more and more convergence of different 3D printing biofabrication technologies. And as a third point, I also think it's important to note that we should, as a field, really move towards xeno-free, so no non-animal derived materials. And I've used Gelma a lot, I still use it, and it's a wonderful material for research, but it also has some limitations for clinical applications being animal derived. So I really hope as a field we will pick this up and develop new materials that are more viable for clinical translation. That's me. Thanks very much for your attention.
Thank you, Ferry, for excellent presentation. It's very creative to see your works. We have two questions from Syed, very intelligent questions, clearly somebody in the field. One question, is it possible to cross-link the 3D printed scaffold for soft tissue engineering? As photo cross-linker produce very stiff structures? That's the first question.
Yeah, so it is with DLP printing, for example, it is photo cross-linking is